A rod of length is pivoted about an end. The linear mass density of the rod varies with the distance according to the condition. Lambda is equal to ax square plus b kg per meter. Calculate the moment of inertia of the rod about an axis passing through its end and perpendicular to the rod. I am imagining that this is a rod. And this is the axis of rotation. Now you take some element dx, which is at a distance x. So what is the formula? General formula is mi ri square. This is continuous distribution of mass. For continuous distribution of mass, in the place of sigma, you will write integral symbol like this. This is lambda dx m x square. Okay, which is nothing m x square, which is nothing but ax square plus b dx times x square. Okay, this is going to be ax square plus b dx x square. This is going to be ax power 4 plus bx square dx 0 to L. Al power 5 by 5 plus Bl cube by 3. That is the expression for moment of inertia. So now I just want to give you a model on linear distribution of mass. This is a linear distribution of mass. Right. Okay. Right. So this is about the first question. We'll work on one more question. What is that? 1 minute. I don't want solution for this. You have a question like this here. Find the moment of inertia of the square lamina of mass m and side L about the following axis. I have already answered this, and just only for the purpose of what you call revision, I am just giving you. I1 is, can you please tell me m is ml square? ml square by 12. I2 or I4 or I3 is the same, which is equal to, yes, which is equal to same as ml square by 12. I told you morning itself. Moment of inertia based one relation. This is the relation. Whether it is a theta, if it makes an angle theta, I about diagonal or I about this line, red color line axis is the same. That's what I've applied there. Right. Next question. Next question is, this is one question which This you need to know. Very good question, actually. Circular hole of radius r by 2 is cut from a circular disk of radius r. The disk lies in the xy plane and its center coincides with the origin. If the remaining mass of the disk is, remember, they have given remaining mass of disk is equal to capital M. For my convenience, I will write this as sigma times, sigma refers to mass per unit area. Pi r square minus pi r square by 4 is equal to M. Sigma times 3 by 4 pi r square is equal to capital M. That is the mass of the remaining disk. Okay, no, I got the point. So what is that? Determine the initial mass of the, what is the initial mass of the, I now know sigma, no? It is nothing but 4m by 3 pi r square. Initial mass of disk is equal to sigma pi r square, which is nothing but 4 by 3 times capital M. Determine its moment of inertia about z-axis. Now you imagine the arrangement in a three-dimensional sense. Imagine the arrangement in three-dimensional sense. Now this is the disk. This is the cut portion. Right. Maybe not good in diagram. Right. This is the disk actually. It should touch like this. Right. Now see, please try to understand what is happening over here is determine its moment of inertia about z-axis. For full disk, moment of inertia about z-axis is mass radius square by 2. M into r square by 2. But here the mass is 4 by 3. 4 mr square by 6. That is the moment of inertia of full disk. For the removed part, whose mass is m by 3. In fact, the mass of this disk is m by 3 and the radius is r by 2. Now, I want the moment of inertia about this axis. Let this be I2, let this be I0. Very clear about morning I taught you the moment of inertia I2 is mass radius square 3 by 2 times mr square. So 3 by 2 times this is MR square by 16. Right. That is I2. So I naught is I1 plus I2. Implies you want I1. I1 means the remaining part. I naught minus I2, which is 2 by 3 MR square minus MR square by 16. That's your answer. Now please confirm from your side, have you understood this or not? Satvik, confirm?
Yes, sir.
Girls, girls,
Yes, sir.
right, right. Next question. We'll work on some questions of moment of inertia, then right. Two uniform solid spheres of mass m1 and m2, radii r1 and r2 respectively, are connected at the ends of a uniform rod of length L and mass m. Find the moment of inertia of the system about an axis perpendicular to the rod and passing through a point at a distance a from the center of mass of the rod as shown. My goodness. The first thing that I need to find out is the system. What the system you have? No, rotation. This is center of mass. A. Total length is L. Center of mass of the rod actually. This is center of mass of rod. Right. 1 minute. I just want to see what is this distance. A plus L by 2 plus R2. What about this? R1 plus L by 2 minus A. That's it. Very simple. Now, see, moment of inertia of this is sphere 1. Sphere 1 is equal to, you said sphere, about this axis, I, what is the formula? Parallel axis theorem is what I am applying. Parallel axis theorem. This is what I am applying. MD square. So I am just applying that. I naught is 2 by 5 M1 R1 square plus 2 by 5 M1 R1 square plus MD square. 2 by 5 M1 R1 square plus. How far is this? We have written here, no? So M1 times R1 plus L by 2 minus A whole square. I2. I2 means sphere 2. Two by 5 M2 R2 square plus M2 times A plus L by 2 plus R2 square. Next, rod. For rod, it is, what is the moment of inertia of the rod? ML square by 12 about center of mass plus MA square. So what is that they are asking is I1 plus I2 plus I3. That's all. So break the problem into pieces and thereafter do that properly. That's all. Okay. So any doubt in this, please ask me. Any student who is having doubt in this, please ask me. If the question is from the center of mass of the system, it is completely a complex question, a different question. Completely a different question. Fortunately, they were asking about this. I think that's fine. Right. Next question. I'm just dealing some models of moment of inertia. Right. Three identical thin rods, each of mass m, length L, are joined to form an equilateral triangular frame. Right. Okay. Find the moment of inertia of the frame about an axis parallel to its one side and passing through the opposite vertex. You know, if we are good at the drawing the diagram, half the question is done. This is how you have the triangle. And this is the axis of rotation. I1, I2, I3. 60 degrees, 60 degrees. Parallel axis theorem. See, please try to understand with respect to this axis, this line is a parallel. So in such a situation, out of all, which is a simple one, you know, I3 is M. That's the question. I3. Any doubts? Just want, if you have any doubt, you will get doubt in this point only. Give me clarity about this. Do you have any doubt? Shrivan, Intalla, కదులుతున్నా. Any doubt? అరే సాత్విక్ చూడు ఒకసారి.
No, sir.
Right. Whereas I1 and I2 is, what is this rod angle theta? It is like ML square by 3 sine square theta. In this case, it is ml square by 3 sine square 60. 60 is 3 by 4. Therefore, total I1 plus I2 plus I3 is ml square by 4 plus ml square by 4 plus 3 ml square by 4, and totally this is going to be 5 by 4 ml square. So if you want any doubt, ask me. Else I'll close this. Next question. టీచర్స్ వర్షన్ వచ్చింది, నేను చెప్పాను కదా వర్క్ చేయలేదు ఇంకా. Find the moment of inertia of a uniform square plate of mass m and edge of length L about its axis passing through point P and perpendicular to it. You want the moment of inertia about this point. We already know this perpendicular axis theorem. We will apply. They will call this as X. We'll call this as Y. So Iz is Ix plus Iy. So ml square by 3 plus ml square by 3, which is a 2 by 3 ml square. Done. Right. Yes. We want to solve this question. ABC is a L-shaped rod made of, you can see that. Okay. What is the moment of inertia of the rod about this axis? It's very simple. Just now we have done, it's a parallel axis. So I is due to two reasons. IAB plus IBC. See, entire rod is parallel to this axis. So all elements are of same distance. Every element in this rod is at a distance L. So simply I will write ml square. But whereas about this axis, you know, BC is a rod, axis is perpendicular to the line passing through one of the ends. ml square by 3. 4 by 3 ml square. Okay, that's all. Simple question. So some of these models, we'll work on this one also. Few models. Find the moment of inertia of a spherical ball of mass m and radius r attached at the end of a straight rod of mass capital M and length L. If this system is free to rotate, passing through the end of the rod, opposite is here. See, I rod plus I sphere, which is ml square by 3 plus sphere. First of all, 2 by 5 mr square plus ml square. That's all. Simple question. It's a very simple question actually. Right? This is a very famous model. Famous in the sense, most repeated question. See, till now, we have done square lamina and we have done the rectangular lamina. This part we don't have actually. But this can be done very simply. Why? Because this is L, this is L. Now imagine if I construct this is rare. Imagine that is a square plate. So total moment of inertia. 1 minute, 1 minute, 1 minute. I will derive it actually. Root to L. Now my point is very clear. This is 45 degrees, for example. Here in this case, undoubtedly it is 45 degrees. Now, we require an element here. Like for example, I am taking length as x. Now consider this shaded point. I'm defining sigma as mass per unit length. This shaded part will have mass sigma is equal to sigma is equal to, if this is x, this is x dx. Sigma x dx is the mass. So now this is at a distance of L minus x. What is going to be the moment of inertia of that element? Sigma x dx m r square. Sigma of dx. X is from 0 to L. That do the integration part very sensibly, like or here x dx, else you will get here as the first part you will get as L power 4 by 2. You will get this as L power 4 by 4 minus you will get this as 2L power 4 by 3. No, hold on. So it is three L's power 4 minus 2L power 4 by 3 times sigma. So the moment of inertia about this axis is 9 minus 8. Sigma L power 4 by 12. What is the area? Half into base into height. So what is the sigma mass per unit area? So therefore, if you write everything properly, you will get ml square by 6. You'll get ml square by 6. Remember, for equilateral, this is the situation for not only for any triangle, if it has some b width about this axis, the moment of inertia now will become about this axis. The moment of inertia will now becomes mb square by 6. Okay. So therefore, for a triangle, I have given the moment of inertia now, which I did not include it in the diagram. So if height is b, mb square by 6. Right. Now you see, I'll do some simple. Now you see, this is the equilateral, this is the isosceles triangle, L. Now try to please understand. So now there are two moment of inertias there. And this we already know, ml square by 3. Now I am going to give you I2 as ml square by 3 minus ml square by 6, which is also ml square by 6, which means if you have triangle, remember this is only for a triangle like this. This is moment of inertia ml square by 6. Trust me, for this also moment of inertia is ml square by 6. So these are very important observations, because at a later stage, when you are applying, you won't get a clarity on what you are doing. Right. So these are very important and standard relations which you need to know. Now I'll start applying torque equation, simple torque equations. Right. And that doesn't mean our total preparation for moment of inertia is done. Just doing partly this, partly that. Right. Now see, in this situation, what is happening here? You have a block of mass M is attached at the end of an inextensible string, which is wound over a rough pulley of mass capital M and radius capital R. Assume the string does not slide over the pulley. Find the acceleration of the block when released. Right. 1 minute. Now in this, note that you have tension here and tension here. The free body diagram acceleration A. Tension T. Now you apply torque equation for this. The only torque is T into R is I alpha. Equation 1. Now T into R, you can take this like a disk. You can take this like a disk. Mr square by 2 alpha. Remember this end of the string and this end of the string. You can see this end and this end length is constant. It is possible when R alpha is acceleration of the block. So therefore, you can write this further as MR A by 2. So tension is MA by 2 equation 1. Equation 2. Free body diagram of the block. From these three equations, you can conclude, yes, the sum gives mg is m by 2 plus small m a. Therefore, a is nothing but 2mg by capital M plus 2 small m. Okay? So that is all about the acceleration of the block. Even you will have angular acceleration also, no, in this. If alpha is A by R, which is nothing but 2mg by R times capital M plus 2 small m. Right. Okay. So this is all about the basic application of equation like this. I'll take one more question. This is the question which I am about to discuss right now. A light rod is connected rigidly with two identical particles of mass m. The free end of the rod is smoothly pivoted at O. Rod is released from rest from this position. Calculate the initial angle. Okay, I'll find. No issues. I'll just see what is the torque. mg. The torque is mgl plus equation 1. And the moment of inertia about this point is equation 2. That's all. You ask that only. మేడం ఈ సెకండ్ మోడల్ ఇవ్వండి, ఒక్క 5 నిమిషాల్లో తీసుకురాగలుగుతారా? సీనియర్ మోడల్ తెచ్చేయండి, నేను క్లాస్ ఆపేస్తాను. రైట్, విల్ టేక్ అప్ వన్ మోర్ ప్రాబ్లం. Right. With this, I'll close the class. Same repetition, boss. Only difference is, see, unlike Newton's laws of motion, constrained motion cases, here tensions will be different. The tension here is a T1 and the tension here is T2. I'm assuming M1 greater than M2. In this case, this is how the disk rotates. So T1 into R minus T2 into R is equal to I alpha, equation 1. Next, remember, since the radius part is the same either side, A is the same on both the sides. So therefore, the free body diagram of this block is simply, this one will be M1Z and this one will be T1 and this is A. Similarly, for the other block, T2, M2G, A. Right. Now, T2 minus M2G is equal to M2A. M1Z minus T1 is M1A, equation 2, equation 3. Right. Let us take the summation of this. We can write it like alpha by R. Of course, hold on. Alpha by R, just like. Now, here, same reason what I expressed today. At this point, R alpha, which is the same as A. So here also you can write R alpha as A. So therefore, this you can write, right, just class, 2 minutes. No, come, sit. Now, therefore, in this case, I can write alpha can be written as A by R. So IA by R square actually. Here you just add it up. These tensions will get cancelled. Finally, you will get M1 minus M2G is equal to I by R square plus M1 plus M2 times. Right. So with this, just closing the session. Right? Any doubts? Boys, any doubts?
No, sir.
Right. I'll post this video once it gets recorded. Right.